All right, topic 16, definition of continuity. Hopefully when I say the word continuity, there's some things that come to your mind, and let's just talk about the types of discontinuity. Can you think of something that would make a function discontinuous, a place on a graph? Well, hopefully you think, well, maybe if the graph had a hole in the middle of it, that would make a function discontinuous. What else? A hole, a vertical asymptote sometimes causes a function to be discontinuous. And finally, a jump. And so those are the three types of discontinuities you can look for. And notice in the example, it says, find any point of discontinuity and classify each as removable or non-removable. So I want to make sure that you know which one of those is removable and non-removable. The hole is a removable discontinuity. Both of these are classified as non-removable. And the reason for that, if you're wondering what that really means, is a removable discontinuity means if you could define a point, could you make it continuous? So if you could have a hole, and let's say this hole was at 7. If I could redefine the point at 7 to be equal to this particular y value, I would then make a continuous function. So that is called a removable discontinuity. Even if you had a closed dot from the beginning, it's can you define or redefine at a particular point to make it continuous. With the vertical asymptote, you can see that even if I could put any y value I want, I could never make that continuous. Or a jump, if you had something like this, again, if you could redefine this point for any y value, it still doesn't make it continuous. That's why this one is the only removable and the other two are non-removable. So if it asks you just to find the points of discontinuity and to classify them, you're going to kind of use your skills from pre-cal, especially when you have this rational function. You're going to say to yourself, well, I would factor the bottom and I would see that I do have a place, that should be a 3, not a 9. I should see a place where this cancels out. So I'm going to have 2 points of discontinuity. I'm going to abbreviate PODs. You're going to have one at -3, and at -3, what's going on at the graph? You have a hole, so that one is going to be removable. But at x equals 3, what's going on? You have a vertical asymptote, so that's non-removable. So that's all that you're supposed to do on that. Don't do more work than you need to do. Now let's look at this second graph. Remember, this one is a one that comes up a lot in calculus. I hope that you could possibly draw that graph right now without even not thinking about it, but I hope you do memorize this graph, because remember, this is the one where, think about it, if you put a number bigger than -5, like if you put 0, notice that you would get 5 over 5, which is 1. If you put 1, you get 6 over 6. Because if it's bigger than -5, what's inside that absolute value is already positive. So basically, you have x plus 5 over x plus 5, which is going to be 1. So you have a graph that's going like that. If you put in a number less than -5, like -6, think about that. -6, you'd have -1 up there, but the absolute value would make it 1 over -1, so that's -1. If you put -7, you'd have 2 over -2, which is -1. So this graph does this. Notice I don't have a closed dot on the -5 because it would be undefined there. And even if I did have a graph with a closed dot, it still is a jump. So you have one point of discontinuity, and that POD is at x equals -5, and it's a jump, so it's non-removable. So those kind of questions, that's what you're going to do. You're just going to figure out the graph, what's going on. Now, if a question asks you to use the definition of continuity, okay, if you see these words, then you have to be a little more formal with it. So the definition of continuity says a function is continuous at x equals c if and only if there are three things that need to happen. And we've kind of talked about this, okay? It's f of c equals the limit from the left equals the limit from the right. Or in other words, let's think about what this means, okay? So, first of all, this one says the function exists. That's what that one says. F of c, I mean, if f of c is undefined, then you can't have a continuous function. These two together, what does that say? Well, those two says the limit from the left equals the limit from the right. This one says the limit exists. And then these two equaling is saying that the limit equals the function value. So it's kind of a three-step thing, but I think writing it like this, that's going to give you a formula or a kind of a script to use if a question says use the definition of continuity to prove f of x is continuous or discontinuous. You have to write it mathematically. So you will see those directions. So let's look at this piecewise function. Again, you see this, I want to see this on your paper, but I want to see that specific for the problem. If you want to write the blanket statement down, that's fine, but I want to see it specific with the problem. So here's what I mean. I'm going to go directly to the specific part since this is sitting right here. I'm looking up here. So looking at this problem, first of all, I look at the individual pieces. Those are both linear, so I know they're going to be continuous everywhere, so I don't really have an issue. Obviously, my issue comes at 2. If it's going to be discontinuous, it's going to be discontinuous at 2. So let me look at that place. So my question is, what I'm going to prove is f of 2, is that going to be equal to the limit as x approaches 2 from the left? Now let me be specific here. Don't just put f of x. Which formula am I going to plug into for the limit from the left? Well, left less than. So I'm going to put negative 3x plus 5. Is that equal to the limit from the right, x approaches 2 from the right, and that would be x minus 3. Okay, so then I just work it out. F of 2, well, where do I have the equal sign? The equal sign is in this function, or this equation right here. So if I plug in 2, that's going to be 2 minus 3. If I approach 2 from the left, I'm going to have negative 3 times 2 plus 5. And of course, 2 from the right is this same function, 2 minus 3. So notice what I get. I get negative 1 there, I get negative 1 there, and I get negative 1 there. And so since that's your work, since all three of those things are the same, you can say, therefore, f of x is continuous. Okay? Because you have just proven, you've proven that f of x is continuous at 2, but like I said, you know it's continuous everywhere else, so you know f of x is continuous. Let's compare that to the bottom example here. Try to write out that first line, okay? So what do we got? Where's our issue? Our issue is at 3. So is f of 3 going to be equal to the limit from the left? Limit from the left would be 3x plus 6, negative 3x plus 6. And the limit from the right is going to be x minus 3. And so what do I get? Well, f of 3 in this piecewise function, that's just 5. Nothing to plug in. I just kind of have to look there. The limit from the left, what do I have? 3, that would be negative 3 times 3 plus 6. And then 3 minus 0, or 3 minus 3 rather, which would give me 0. So what do I have? I've got negative 3 there, and I've got 0 here, and I've got 5 there. So, okay, this is weird. So what's going on? Well, this piece right here, I mean, the function exists, yes, but with these two, the limit from the left doesn't even exist. I mean, the limit, the overall limit doesn't exist because the limit from the left and the right, those don't exist. So you can say, therefore, f of x is discontinuous at x equals 3. Now, if I ask for the reason, you could say, because on your homework you have to tell what reason, and here are the reasons. And go in this order. Does the function, you kind of tell the first one that it doesn't satisfy. Does the function exist? Yes, I got 5. But does the limit exist? No. So since the limit at x goes to 3 of f of x does not exist. Okay? This right here, because these are not equal, it does not exist. Now the third example, and I'll just chain, this is a different problem, so no, it's not this one. But the third case is when, let's say you had when you wrote this out, you had something like this. Well, the function exists. In this case, if you had this, the limit would exist, but the function does not equal the limit. The function would equal 5, the limit would equal 0, and so that's the third case, that the limit doesn't equal the function value. Make sense? So, on this next one, if you're given a graph, these are going to be very quick ones, because all you're doing is you're putting the reason for it being discontinuous, or you're saying that it's continuous. So see if you can match up. Again, I hope you can read that mathematically, what these A, B, C, and D are saying. And so I want you to match those up and see what you get. All right, number 4. That one's pretty, yeah, it's like, okay, what's wrong with number 4? Nothing. Number 4 is continuous. So which one of the letters is it? Well, here, letter D is the limit. Okay, the function exists, the limit exists, and they equal. So that is true if and only if the function is continuous. So that one's going to be D. Now the rest of them, 5, 6, and 7, they're all discontinuous at C, but what's the reason? So let's look at C. Okay, and remember you kind of go in that order. The function exists, the limit exists, and the limit does not equal the function value. So on 5, you go, well, the function doesn't even exist. So that would be letter A. That's what this one is saying. F of A does not exist. The function doesn't exist. Number 6, does the function exist? Yes. Okay, because you have a closed dot at C. Does the limit exist at C? Yeah, because the limit from the left and the limit from the right are the same. But the function and the limit are not the same thing. So this one is going to be C. And then process of elimination, you know what the last one is, but just to explain, the function exists. Yes, you have a closed dot, but the limit does not exist because the limit from the left and the limit from the right are not the same, and so that would be letter B. Now the last statement in your notes is purely that, a statement, and it seems like it doesn't have, you're like, okay, if you have two functions that are continuous, all of these will be continuous as well. So f plus g, f minus g, f times g, the composition, multiplying one of them by a constant, and even division, provided that that bottom function doesn't equal 0. Okay? all of those would also be continuous. And again, that doesn't seem to have much oomph, but a lot of times you don't have to use the definition of continuity, but you have to state that the function is continuous. And here's what I'm saying. If I ask you if h of x was, if you had to look at that and tell if it's continuous, you'd go, well, shoot, I don't know what that graph looks like. And frankly, I don't either. I mean, I couldn't draw that, right now perfectly. But what you do know, if I said, guys, could you draw me x squared? You go, well, it's a polynomial. Polynomials are always continuous. Okay. Could you draw me sine of x? You go, yeah, that's the one that's doing this, it's continuous. Can you draw me e to the x? That's exponential, and it's doing this, so it's continuous. So the point is, if you know each piece is continuous, all I'm doing is adding and subtracting them together. I know that h of x is continuous. I can state that without, if I need to do other things, I can prove to you that h of x is continuous, or I know that h of x is continuous, and I can just state that. All right, so that's what you are doing in your homework, things like that, and a little bit of review. So good luck.